Hello, everyone, and thanks for joining the Lattice Developer Conference. The topic today is about an introduction to FPGA. So if you are new to FPGA and you want to learn more about the FPGAs and how they are constructed, architected, this is a good course to follow. One of the questions that you may have is what's the advantage of FPGA versus more traditional discrete devices? For implementing board level logic, some reset logic, or some control logic or housekeeping logic for a board. This training is meant to get you introduced to the FPGA technology from the basics. So we're going to start from the basics, going through the architecture, building blocks, functionalities, and some practical steps to get you started with your first FPGA design. So if you have any question, please use the Q&A widget to submit it. We'll try to answer all the questions at the end of the presentation. So my name is Murad Akama. I prepared the content of this presentation or this training, and I will be walking through the whole presentation. I'm currently part of Lattice Insights, the training team for Lattice. As a content developer and a training instructor, I have over 20 years of experience within the semiconductor industry, of which more than 15 are with Lattice in different responsibilities. So as an application engineer, field application engineer, and strategic account management. My main field of expertise relates to Lattice hardware, software tools, FPGA architecture, design techniques, best practices, and timing constraints. So in terms of academic background, I have a EE in electronic and a master's degree in microelectronic with an MBA in management from the University of Quebec in Canada. So the agenda for today has 5 different sections. So we're going to start the first section to cover the advantage of using FPGAs versus more traditional discrete devices. We will detail the impact of logic consideration on area, design testability, power consumption, and also highlight some of the key features that an FPGA may bring to your system, like flexibility and upgradability. And then in section 2, we'll talk about basic gates and logic elements. So we're going to go from the basis in terms of logic levels and signals for the IOs, the gates, how they are constructed from transistor, combinatorial logic, synchronous logic. Why do we need synchronous logic? Why do we need combinatorial logic? And embedded memory also, which is a main component, a very fundamental component in FPGAs. Then the third section will be more about an example of architecture for the ICE40 Ultra Class, which is the most basic FPGA from Lattice, where we're going to go through the architecture element that includes the lookup table, the PFU, so and understand all these terminology about the different things that we use in FPGA, what's the IO structure, the memory structure, the PLLs, and some of the hardware function like I2C, SPI, DSPs, and internal oscillator. We have a brief section on design techniques, so we cannot cover all that in 1 hour session. So we're gonna talk a little bit about some of the design techniques that you can use in your development to enhance throughput. And the last section will be more about a high-level overview of all the different FPGAs that we have in Lattice and their end market or the target end market that we can use them for. So let's start with the advantage of FPGA implementation. And you may be asking the question, why should I use an FPGA? What's the advantage of this technology? So as you will see in the next couple of slides, FPGA represent a couple of advantages that we're gonna go through, especially today we have a very affordable technology at very low power and high integration in terms of features. So they become more relevant to be used in all kind of application, especially recently where we've seen the shortage in semiconductor component. The trend was to use more generic device so we can replace it easier, and that's what we can cover in this section. So, as you know, FPGA stands for Field Programmable Gate Array. It is a sea of gates that could be used to implement any conventional logic, like seen in the slide. So you can integrate SPI, A2C, PLLs, PWMs, glue logic, some of the 74X type of logic. They are all could be consolidated in one FPGA. And the smallest FPGA that we have in Lattice, it's called the ICE Ultra Plus, ICE 40 Ultra Plus. It's a 2.1 by 2.5 millimeter and can integrate up to 500,000 logic cells. So we're going to see this terminology later, but that's a lot of logic that integrate multiple of these components in the same device. This is a device that is offered, for instance, in multiple packages. So it depends on your needs for your board or the PCB technology that you are using. You could be using wafer level chip scale package or the QFN package or other packages. So for each family, there is multiple packages that are used. But the ICE 40 is the smallest, and you can grow up from there to the Certus Pro NX, which is up to 100,000 lookup table, integrates much more primitives or much more components into the device. It also can integrate some SoC implementation, system on chip implementation. We're going to see that a little bit later. And Avant is our latest family of devices that can go up to 500,000 lookup table with memory, DSPs, PLLs, and also can integrate system on chip. So one of the main advantage of FPGA is their I/O flexibility. So all the standard that we see in this slide, whether it's SoundWire, SPI, I2C, UART, DSI, PDM, they are all could be all implemented within the FPGA or could be interfacing to the FPGA, and almost any pin in the FPGA can be configured to support any of these standards. So some of the application that you may see would use an FPGA as signaling aggregator, so to minimize the number of traces in the on the PCB, and also have smaller connectors, so you can aggregate multiple signals within the FPGA and send them across different ports or within the same board to different component within using the signaling aggregation application. So the reliability is another aspect, and testability. So without going through the details or a lot of details in terms of the reliability, when using an FPGA, you have a single point of failure. There's multiple points of failure with discrete. These also have a ripple effect on testability of the design. In fact, you can perform more thorough testing of the functionality that you integrate in the device. And you can do it at different stages of the design. So you can do it even early in the design process by using some of the functionality, simulation functionality that are integrated with the tool. So you can do functional simulation to validate the integrity of your logic. You can do RTL simulation, timing simulation. And the nice thing about using the FPGA is all the timing are pretty well defined within the FPGA. So when you do timing simulation, you are pretty sure that your device will behave as expected, given that the simulation works, provide the right result. There's also the possibility of having a logic analyzer. So there's an integrated logic analyzer capability within the device. It's called Reveal. And Reveal allow you to probe internal nodes into the device and be able to display them on the screen and debug your design as you go through the development. So the other, I think, important advantage of FPGA is their flexibility and adaptability during and after design. So FPGAs are based on SRAM technology. So they are infinitely reconfigurable, which is an advantage. It offers a lot of flexibility. So you could, during the design phase, you could have to select to support multiple I/O voltages and select the I/O voltages that you need depends on what is available on the board. You have internal logic that is customizable to adapt to different requirements that you have. They could be evolving requirements that you have through the design process. You could also accommodate easier board layout by selecting the pins that are more adapted to the PCB, to the component that you have in the PCB. And the other, I think, advantage is you can accommodate multiple variant of the board with the same layout. So the FPGA configuration could be different for each board to enable different features. So this could even save you some PCB respin for between different variant of project. The other thing is the same HDL code could be targeted to multiple devices. So once you have the design done, it's operating on a device. If the device goes to end of life, you have always that source code that you could target to a different device and have a quick turnaround in terms of having a new board released. The other, I think, advantage that we see a lot in the industry is bug fixing after board release. Logic could be upgraded and fixed or could be accessed remotely. You could fix existing bugs that you may experience in the field. You could also change the content of the FPGA after the board release to fix some of the bugs. And this feature could be also applicable to the upgradability. So you could do field upgrade for the device in the field. And you could also add some feature and functionality after the board release while the board is at the customer side. So field upgradability is another advantage. So talking about cost, I mean, the Lattice, offer very competitive devices, but also the price of the different discrete component versus single device could have an advantage in terms of a lot of factors. Usually we account for the cost of the device themselves, but we don't account for the testability. So testability is another aspect that could save a lot of time. And while developing the device, there is also the capability of doing GTAC boundary scan, which allow you to test the board at a higher level without the need of having a bed of nail. The price of a pick and place, I mean, you have hundreds of components and pick and place in the manufacturing process is a small amount of cents per device, but that adds up. There is also the simpler board layout advantage that could be saving some cost also when you develop with FPGAs. And the price associated with multiple board variants. So if you can have the same board layout that could be used in multiple projects, that will obviously save you cost. So these are all aspects that could make the overall cost of ownership or the overall cost of developing a board lower than a discrete component. So that brings us to the basic gates and logic elements. So in this second section, we will talk about logic levels and signals, gates that are made from transistors, combinator logic, sequential logic, and embedded memory. So why do we need all these components in an FPGA, and going through the from the basic to talk about the architecture that is involved in all of these components. So with the first thing is logic and level and signals. So as we said before, the FPGA is very flexible and all IOs can support multiple different voltages. And in order for the FPGA to see a 1 or 0, there is certain rules that has to be satisfied. So, and the FPGA is compliant to standards that are available in the industry. So if we take the example here for LBCMOS 3.3, there is VIL, VOL, VIH, and VOH, which are the voltages that are need to be satisfied in order for the signal to be recognized as a 0 or as a 1. So for 3.3, for instance, a logic 0, for logic 0, we need to have a signal between 0 and 0.8 volt. And for a signal to be recognized as a high or as a 1, the voltage has to be higher than 2 volt, or between 2 volt and 3.4 volt. There is a maximum voltage, obviously, for all the IOs. And the same thing will apply for output. So the device will output a signal that is compliant to the standard. Same thing for LBCMOS. So the VIL is 0.7, the VOL is VI high is 1.7 to 2.6. And the V output high or low are listed in this table. And this is a table that we take from the datasheet of each device. You're going to find all this specification. And you can see for LBCMOS 3.3, these are the voltages that need to be satisfied in order for the signal to be recognized. Anything in between is in the gray area and will not be, we are not sure, we cannot guarantee that it is recognized as a 0 or as a 1. This is obviously compliant to the standard, to the industry standard. So LBCMOS is defined and we comply to that standard. So what we see here is a simple gate made of transistors. So it's an inverter actually. So when you have a 0 on the input A, that input is inverted. So this transistor is active and the output will be high. If the input is high, then this transistor is active and we have a 0 here because this B signal is pulled down. So this is just a simple basic inverter, and that's kind of the truth table that is associated with it. If we get a little bit more complex and have an OR gate, the same principle apply. When either of A or B are active, then, or any one of them are active, this signal will go to ground, and then we have a transistor that is tied active. This transistor will be active, and the output C will be high, and so on. And since we have 2 inputs, we have 4 combinations here. So the number of combination will depend on the number of inputs you have for this type of logic. So the only time you have a 0 when both input A and input B are 0, and in all the other cases you have a 1 as an output, which is the operation of an OR gate. So obviously, if you have more inputs to your logic, then there is more combinations that are possible. It's 2 power n in terms of combination that you could build out of the logic that you have. So that brings us to the combinatorial logic. So what is combinatorial logic? Combinatorial logic is defined as digital logic that is implemented by Boolean circuit, where the output is only dependent on the input. Okay. So all the gates that we've seen in the previous slides and more are combinatorial logic, and they operate depends on the input that we have on the logic. So the output is only dependent on the input A and B, in this case for the AND gate. And the output will take a little bit of time to change. So that's what we call the TPD, the propagation delay through the combinatorial logic. So in this timing diagram, we have A and B, and we see that A changes to a low. We have an AND gate, so the output will be changing to a low here, but it will change a little bit after this delay or the TPD. Propagation delays will depend on the device characteristic and the level of logic implemented. It is usually in the order of nanoseconds. So every device will have a different propagation delay, depends on the technology that is used and depends on the number of level of logic that you may have in the design. So combinator logic is needed in any design. It's required. That's how you build all your logic, but it has limitations. So we cannot rely on combinator logic to have a predictable design. Why? Because first, the delay is not predictable. So for each technology, that delay may be different. You're going to see in the FPGA, having the combinator logic implemented in the device could have different delays, depends on how it is implemented. And there is also what we call the undesired trigger. So if any of the inputs change for a small amount of time, even if it is noise that you have on the board, then the output may be glitching, going to 1 and back to 0, which is not reliable, and you cannot use it to build your logic. And like I said, in terms of unpredictable behavior, when the technology changes, so you have that TPD that will be changing. There is also variability when you change more logic. It's not the same thing if you have a 4-input AND gate or you have a 6-input AND gate, depends on the architecture. This delay will be changing also. The speed grade and the package will have an impact also on the TPD or on the combinator logic. So the question we have or we may have is, how can we make this design more reliable? So that's where we get to what we call synchronous logic. So it's a logic in which the change in state are synchronized to a clock signal. It's like the heartbeat that everybody will be synchronized to, and any changes in design will be related to the clock. There are obviously limitations on how fast you can run the design, and we're going to see this limitation, how to calculate the Fmax, but it's more reliable way of building your logic. So let's dive into the synchronous logic and the basic components that are involved in synchronous logic. So the flip-flop, or what we call register, is the most important or the fundamental element that we have in a synchronous logic. A flip-flop will have a D input and a Q output, and the truth table is represented here. So the Q output at time T and Q output at time T plus 1. T plus 1 is after the clock edge. So if you have a 0 in the D input and 0 at time T in the Q output, then after the clock it will stay at 0. But if you have a time T Q output as a 1 and you have a 0 in the input D, then the output will be changing to 0 after the clock. So that's kind of how the operation of this flip-flop is. But there is constant timing that need to be respected, or timing that need to be validated in order for this flip-flop to operate reliably. So the timing are listed here. So if we look at the clock, a timing diagram here, so we have the clock with the rising edge. So we could be triggering this flip-flop on the rising edge or the falling edge, depends on your design. But there is these two timings that you see here, the setup time and hold time, that need to be satisfied in order to make sure that the flip-flop operate in a reliable manner. So what is setup time? Setup time is the minimum amount of time that the data need to be stable before the clock edge. The hold time, on the other hand, is the minimum amount of time that the data need to be stable after the clock edge. So if we satisfy these timing, we should have a reliable operation of the flip-flop, and that will happen on each clock cycle, and has to be satisfied on each clock cycle and each flip-flop that you have in the design. The other timing that is important to take in consideration is what we call TCO, or clock to out. So from the time the clock edge happen, it takes a TCO to have a stable output of the flip-flop. Before that time, the data may not be stable and not reliable. So we have to take in consideration all this timing in order to make sure that our design is reliable. So how fast can we run our design? So given that we have a clock and a period of the clock that is X nanosecond, depends on the frequency that you have, it's 100 megahertz, then we have a 10 nanosecond clock period, and we have to make sure that the data travels safely between the first flip-flop and the second flip-flop between that time. So that time will include the TCO, which is the clock to out, so the time it takes for the data to be stable at the output of the flip-flop, plus the combinator logic that you may have, or the number of level of logic that you have in the design, plus the setup time and hold time. So that's how all these timing is constructed, and the shorter this time, the faster the design can run. And in order to calculate the Fmax for this design, so we the tool actually will calculate all this timing and will allow you to have the Fmax, that the maximum frequency that you can run at. But it's the basic formula by Fmax equal 1 over the X time that we calculated multiplied by 1000 in megahertz. So if you have a 50 nanosecond delay of all these components, then you may be running your design at a maximum frequency for 20 megahertz. If it's a 10 nanosecond, then it's 100 megahertz. So if you run it faster than this, then the design becomes more reliable. This is something that will be provided by the tool when you do the design, your FPGA design. So in the synchronous logic, I mean, we've seen in combinatorial logic that the output is only dependent on the input, whereas in synchronous logic, the output could be dependent on the input, but also on registered output. So there could be feedback that will be sent to the logic in order to generate new logic. So that's the main difference also between synchronous logic and combinatorial logic. So let's take an example, basic synchronous logic example here. So let's say we want to control, let me take my laser pointer again. So we want to control a boot up reset for the digital board that has 3 power supplies. So 3.3, 2.5, and 1.8. So each one of these power supplies will have a power good signal. So once the power stabilized to this voltage, then there is a power good signal that will be released. We need to build some logic that generate a reset signal under this condition. So reset goes low after a minimum of 20 nanosecond delay after all power supplies are stable. And that means PG, or power good, is high for all of them. And we have for this design 100 megahertz clock, and we have these PG signals that are connected to the FPGA, and this is the reset that go into the CPU. So how can we implement this simple function? So first, what is clear here is that we need to have some combinatorial logic, which is an AND gate between all these PG power good signals. So when all these power supplies are good, then we have to generate some way to have a predictable delay to release the reset. So in this graph, we have all these power good signals, and remember the TPD. So after all they are good, there is a small delay that will release this power good signal, but that's combinatorial. This delay is not predictable. And we could, in order to have a synchronized sequential logic, we have some cascaded flip-flops that we could use for predictable delays. So we know that these flip-flops will operate at 100 megahertz. So that's a 10 nanosecond delay. And you can see if your D input, which will be the output of all this combinator logic, is going low, for instance, meaning that all the power supplies are stable. Then Q1 will go low after this for the first time on the first rising edge. Then the Q2 will go low after the second clock edge on the second flip-flop, and then third flip-flop will have 20 nanosecond, and that's a minimum 20 nanosecond between when the time all our power good are stable and the time we release the reset to the output to the CPU. So we actually, if we want to implement this in FPGA, we're going to have a similar circuit like we see here. So we have all these signals coming into the FPGA. We have the AND gate. We have the inverter that is not in the previous slide, and the output of the inverter will go through the series of flip-flops. So the first flip-flop will do the synchronization of this combinator logic to the clock domain, to the clock. And then these two flip-flops will provide the delay of 20 nanosecond, the minimum delay of 20 nanosecond. And then our output will go to the CPU. And this way we have a predictable, reliable design that will work for any technology and will be always operational no matter what you change if you specify the timing of the FPGA. So all this logic takes 3 logic cells to implement all this. And the device that we're going to talk about later on will have 5,000 logic cells in it. So you can imagine the amount of logic that is available in the smallest device. So embedded memory. So this is another fundamental element in the FPGA, and we'll start from the basic, just describing the memory block. So the memory block could be thought of as a collection of registers. So you could have each one of these bits as a register, and you have 16 of them if you have a 4 input address line. We actually use address lines in terms of address each one of these bits that you have in the memory block. So for each one of these cases, we will have an address. So in order to address bit 0, we have address 000, bit 1 is 001, and so on. So, and in each one of these memory blocks, we can store a value, a 0 or a 1, okay? So let's say we have this example. We have this memory block with all zeros, but the last case that has a 1. So in order to address this last memory location, we have to provide, obviously, the address is 111. So if we put 111 on the address line, we have 1 as output. If we put any of the other value, then there will be 0 as an output. And this is represented in the truth table that we see here. We have the 4 input A, B, C, D, and the output. And the only way to have an output 1 is to have the address line as 111. So this is basically an AND gate, and that's the basic element on how all the logic and the FPGA are built. So based on memory and programmed memory for certain function. So you can imagine that with this basic building blocks that we have with the 4 input lookup table, we can build any 4 input logic that you may have. And associated with the flip-flop, that will represent the basic building block for an FPGA. So this is the LAT4 or 4 input lookup table. Then we have the synchronous logic, and this will be called actually a logic cell, as we're going to see in the next slide. So you could be doing your combinator logic and going out without registering the output, or you could be going through the register. So let's say you have an 8 input equation that you need to build, then you may have to have two or three of these to build your logic. Then you go through a bypass path, and then you go to the next stage and build your logic. Then you go through the flip-flop to build your synchronous logic. So as we said, so the four-input lookup table, so that's referred to in the literature for LAT, usually. So it's a four-input lookup table. If we add to that the flip-flop, then we are talking about a logic cell. If we add two of these, there is common logic that is shared between two logic cells, and that will be called a slice. It's a group of two logic cells. And the PFU is actually a collection of 8 logic cells or 4 slices. They are grouped in what we call a PFU. So each slice will have a letter A, B, C, and D, and the collection of all these will be placed somewhere in the fabric. And there is routing resources that will go through all these PFUs. So that's how the FPGA is built, and you have the I/O banks to go in and out of the FPGA, but all the logic is built in these PFUs that you see across the board. The nice thing is this architecture is very scalable, so you can increase the number of PFUs to have a larger device. So now that we are familiar with the basic architecture of an FPGA, we can take an example of Lattice FPGA, namely the ICE40 Ultra Plus, and try to go through the different components that are integrated into the FPGA, or the different primitives that are used in the FPGA. And this is something that I got from the datasheet, from the ICE40 Ultra Plus datasheet, and the architecture of the FPGA, or the different building blocks of the FPGA. As you can see, all these rows will represent PFUs, obviously, and you have multiple components that are integrated. So these block of RAM. So on top of the memory that is in the lookup table, there is also block RAMs that are embedded into the fabric. And these two types of block RAM, we're going to see them later, but these small blocks and large block RAMs that are available to the user. There's on-chip DSPs. So DSPs could be very expensive in terms of lookup table or logic to be implemented. So these hard DSPs that are built in the fabric also to be accessible. And these DSPs could be, could support a different format. They could be operating as a multiplier, as a multiply accumulate, as an accumulator, or other substructure, also other modes that are available. There's also the hardened function. So I2C, they are hardened IPs into the fabric, and there's also SPI IPs that are hardened, plus on-chip oscillator. So these high-frequency oscillator and low-frequency oscillator. We're going to go through all these components in a little bit more details without getting a lot of details on this, but just to give you some perspective in terms of the complexity that is associated with the architecture of the FPGA. On top of all that, you obviously have the I/O banks. There's multiple I/O banks per device. And you also have some hardened IPs, like the PWM IP that is hardened, or some I/O flexibility or I/O delays that are hardened, and so on. Configuration logic is hardened also. So there's a lot of other features that are available in the fabric. So if we look at the PFU, and this is the real architecture from the data sheet, so you're going to see each one of these PFUs, like I said, it's a 4-input lookup table plus a flip-flop, but you're going to see some carry logic that is going across the different element, or the different logic cells that you have in the design. There's the register, there's the option to bypass the register, and there's the input for clock enable, and reset that is shared across the PFU. in terms of I/O cells, so in the I/O cells, it is the most basic I/O cell structure. So we have the I/O pod that you see here. So going into the chip, you have the I/O buffer that will be configured to the I/O standard that you need. You could go into the fabric directly. You could use this pin to go to a clock tree. You could use this resistor to have an input that is registered at the I/O. Or you could have some ice gate, which is kind of a low power option that you use to avoid the having the I/O floating and minimize the power consumption. The same thing happened on the output side. So you have the options to go through the register or to bypass the register, then going through the buffer and going to the output pad and the output enable also. You also have some option on the I/O to have pull up, pull down, bus hold. So ICE40 has only the pull up that is available in this picture. But you could configure each I/O to have a different pull or I/O option, depends on the needs. Some I/Os offer also open drain. So the large RAM or these embedded block of RAM that are available in the ICE40, so they are 256 kilobit each, and they are configured in 16K by 16, but you could change this configuration to different modes. So 256 by 16, 512 by 8, 1024 by 4, and 2048 by 2, and depends on the configuration. There is multiple primitive, and these are the primitive that are used within the tool to configure the memory. These are single port RAM, so you can only write from one side and read from the other side. You cannot read and write from both sides, so it's a more simplified version of the memory for the ICE40 for the large RAM. You also have smaller blocks of RAM. These are 4 kilobit of RAM that are available. Other family obviously have different structure. The Certus Pro, for instance, or the Nexus family, they have 18 kilobit block of RAM, and the Avant family, which is the largest family, they have 36 kilobit of RAM. But it's basically configurable memory based on your need, but with the capability of doing true dual port, meaning that you have a write port and a read port, write and a read port from each side. And you can configure to different widths also. The PLLs, so there's multiple PLLs in the fabric, and these could be used to synthesize clocks from one main clock. So you have your reference clock input that will get into the PLL. It's a VCO-based PLL, and you have multiple dividers that will be used to calibrate or change the VCO and generate the required frequency on the output. So these multiple dividers, just to simplify things, there is a div R, div F, and div Q. So it's a reference clock divider, feedback divider, and VCO divider. And they are configured to have a value between 0.15 or 0.127 for the different divider. And each family will have a different setting, obviously. But in order to calculate the output frequency of a PLL, then you have the input frequency multiplied by the div F plus 1 and divided by div R plus 1, basically for this ICE40 PLL. DSP blocks, it's an eye chart that we see here. I will not go through the details of all this, but just making sure that you understand that it's a very complex block with hardened multipliers that are built in, and also register, input register, pipeline register, and some flexibility in terms of how to cascade some of the blocks that you have there. And as I said before, implementing this in logic could be very expensive. One 18 by 18 DSP could be using up to 500 logic cells. So by having this hardened function, you obviously optimize the number of resources that are used and have the rest of programmable logic area to your tune to your need or to implement your own logic. The ICE40, like we've seen before, we have I2C. And these I2C, even though they are hardened I2C, they are configurable. So they support clock stretching. They can operate up to 400 kilohertz. And they can interface to customer logic through the system bus. So the system bus that will connect it to the logic here, and you'll be able to interface to it. The high speed or the embedded oscillator, high frequency oscillator and low frequency oscillator, also configurable. So you can configure a divided version of these. The low frequency is 10 kilohertz. The high frequency is 48 kilohertz. And you could use them by just instantiating that component in your design, and you'll be able to use the oscillator in the design. No need for external oscillator. You may be, sometimes it's useful to have some watchdog or some internal logic that's required to operate even before the main clock is available. So you could use these clocks to operate that logic. SPI interface is a full duplex data transfer. It has mode fault error flag and CPU interrupt capability, double buffered data register, serial clock with programmable polarity phase. It's also can communicate through an 8-bit wide system bus to the rest of the logic. And you can refer to the datasheet for much more details on each one of these components. So there's actually technical notes for each one of them to allow you to configure them and use them to your needs. So now that we understand the basic logic, the advantage of an FPGA, and how a simple FPGA is constructed, we switch gears and kind of get to design techniques. Like I said in the beginning, I will not be able to cover a lot, but at least having some simple example here that allow us to go through pipelining, parallel structure, and loop unrolling for enhancing throughput for a design. Just to say that the way you do your design matters. So these trade-offs to do when you implement your design. And based on the trade-offs, you may prefer one implementation versus the other, but we're going to go through some examples here. So what is throughput? So throughput is the amount of data the amount of data processed per clock cycle. It is expressed usually in bits per second. On the other hand, the latency is the time taken for an input to go through the combinator logic or to propagate through the logic, user logic, and be ready at the output. It is expressed usually in units of time. It's the number of cycles or number of clock cycles. So the obvious question is, how can we probably get higher throughput if throughput is important to you? So let's go through a couple of examples. So when we talk about higher throughput, we talk about increasing the Fmax. And we've seen in previous slides, in order to increase the Fmax, we have to make sure that the logic between two flip-flops is smaller or shorter the time that is required to process the logic between two flip-flops. So if we want to have a higher frequency, then we may adopt one of these techniques. We may add pipelining register, meaning that we divide the logic in multiple pieces, so we are able to have things processed, new data processed while the old data is still going through the pipe. We could also adopt parallel structure. I mean, obviously, when you do that, you use more resources, but at the expense of resources, you have a faster design. And you could be unrolling the loop. And we're going to see all these three examples in the next couple of slides. So let's take the example of a design where we want to multiply A, B, C, and D. So each one of them go through a register. Then we have the multipliers. So these are the three multipliers. So we multiply A and B. That's multiplier 1. Then we multiply the output with a multiplier 2, and then so on, and we have the output. Obviously, in this case, we have throughput of 1, and we have a latency of 1. So every clock cycle, we're going to have a data, and we don't have to wait for the data to be available. So once A and B and C and D are clocked, then the next clock cycle, we're going to have the output changing with a new value or with the output of our logic. We're using 5 register. But as you can see, there's 3 multipliers that are cascaded, which kind of make it a little bit hard to go through all of these 3. Then the delay is longer. Then we can only operate at 75 megahertz. Okay. So the same design with pipeline register could be done this way. So we could insert a register between all these DSP blocks or these multipliers. So we have the first multiplication done, then the second multiplication done, then we register, then the third one, and so on. Obviously, once we clock the data A, B, C, and D at the input here, we have to wait for 1, 2, 3 clock cycle to have the data output or available at the output. So there is a latency of 3 to have the first data out. But if you don't care about that, I mean, latency, that's fine for you. But after this latency, then every clock cycle we can have an output, because we are processing new data while the old data is going through the pipe. When we are adding this register just to calibrate the data to make sure that the multiplication is done the right way. So, but in this case, you see the number of registers. So we are using 5 registers here. We are using 10 registers here, but we operate at 163 megahertz, which is a much higher frequency. So if throughput is important and latency is not important, then this structure may be a little bit more adapted to your need. Okay, let's take another example for parallel structure. So we could do the same thing by having 3 multipliers, but in parallel. So we could, instead of having 3 cascaded multipliers, so we could multiply A and B, C and D, and multiply the output of M1 and M2 together to have the output. Obviously, here we have no resistor in between, so the throughput is 1, the latency is 1, and the number of register is 5. It's like what we've seen in the previous one, but we shortened implementation than the previous implementation we've seen at 75 megahertz. But if we add a register in between, so if we, let's say, add a register between the M1 and M3 and M2 and M3, then we have a latency of 2 now, because we have to go through these extra register, but we'll be able to run at 195 megahertz, which is a much higher frequency. So depends on how you do things, depends on how you implement your design. It has an impact on the frequency, operating frequency, and depends on your need also. So let's say in this example, we have a very limited area. We don't want to implement things in parallel. The resources are very limited. We don't have a hard multiplier, for instance. We only implement that in logic. Then we may opt for having a 4-to-1 max. So we have all the inputs and we multiply. First thing, we do the multiplication of A, then the output, we multiply it by B, then the output we multiplied by C, and so on. So in this case, we have a latency of 4, but also it takes 4 clock cycle to have the multiplication of A, B, C, and D completed. We can operate at 195 megahertz, but the actual throughput that you have here is 195 divided by 4 because you have to go through the 4 inputs in order to complete the multiplication. This could be very well adapted to a small area, but you could also, if you have this implementation, you could go to similar implementation that we've seen before by enrolling the loop, so removing these marks, 4-to-1 marks, and replacing it with multipliers, which will allow you to run at a higher frequency. And if you add the pipeline register, then you have even a higher frequency than 122 megahertz. So these are the different ways of implementing the same design, and you see that the selection of the architecture or how to implement it has an impact. Selection of the pipeline register has an impact. Selecting of the unrolling the loop has an impact on resources and Fmax and latency and throughput. So just to say that it matters how you write things or how you architect your design. So we have seen so far the basic building blocks of an FPGA, how they operate, and some of the basic design techniques that could be used for better throughput. Just to say that the architecture decision has a significant impact on the performance and the power and the resource utilization. So there is much more material that is available on this subject on the Lattice Insights, which is the official training platform. The Lattice portfolio is much more richer than what we've seen in these slides, and we can try to give you a high-level overview of the different device family that are available. So Lattice offers a wide range of FPGA product that suit different industries. I mean, the selection of one family or the other depends on different factors. Just to name a few, it could be the logic density, the number of IOs, the memory requirement, DSP requirement, and so on. And to adapt to the different market segment needs, each device will have certain features that are best suited for that market. So as you can see here for the smaller FPGA or small density FPGA, so AS Ultra Plus is the one that we've seen in this presentation. We also have a video connectivity product where these are more adapted to video implementation, mainly MIPI, CSI, DSI requirement, with Crosslink UNX, which support USB also. Control and security, the Mark family is very well adapted to that segment. And general purpose FPGAs, they could be used for a variety of industrial, automotive, video application. Also, these are a little bit more larger devices, but stay in the small FPGA density device up to 150,000 logic cells. And on the higher end or the mid-range FPGA, we offer the Avant EEG and X, which go up to 500,000 logic cells, and could be also targeting multiple end markets. You can refer to the documentation for much more details. As you've probably seen in some of the Lattice communication, so Lattice is the industry leader in terms of low power FPGAs, and they have products that are very well positioned for various growing markets. So we have products and solutions actually that are targeted to communication, computing, industrial, automotive, and consumer also. So please make sure you get in contact with your local Lattice person to get more details or to get further details on any one of these market segment or FPGA needs for these market segment. Also, there's the Lattice Insights website. It's a new initiative that will allow you to have all the information that you need, all the trainings with pre-recorded trainings about different subjects. I kind of listed here some of the training that are available for ICE40 Ultra Plus in terms of better understanding the architecture, some of the development board videos, as well as PLLs and clock network and so on. So you can visit the Lattice website and encourage everyone to sign up in the Lattice Insights for free and have access to some of this material. Some of them will be career-based, but that's, I mean, majority of it is free material that is available to you for and that kind of brings us to the summary. So what we've seen today. So we've seen that the use of FPGA has multiple advantages. Obviously, logic consolidation, flexible IOs, better reliability and testability, flexibility in the field and field upgradability and bug fixing. So it's all these advantages that could not be available from discrete component if we compare that to some of the discrete component. We've seen also the basic building blocks for an FPGA. So in terms of combinator logic, synchronous logic, how they are built, and the memory blocks also, and how they are used to construct logic. We had an example of Lattice FPGA architecture, ICE40, and we've covered some of the design techniques in terms of throughput versus latency and the impact on performance and area of the design. Just keep in mind the ICE40, what we've seen in this presentation is the most basic architecture from Lattice. So these much more complex devices, you can refer to the website or Lattice Insights portal to get more details on the different solutions that are available. There's also solution suites that are available for different markets like SenseAI or Drive for different segment of the market, which we have a collection of IPs and tools to get started pretty quickly in implementing Lattice solution in your environment. So that concludes the presentation. And I don't know if we have enough time to go through all the questions, but I'll make sure we take note of all these questions and get back to everyone after the session. Thank you again for being part of this presentation, and hope to see you in other presentation today. Thank you very much. Have a great day.